Okay, so today's lesson, we kind of go back, and this is good because it reviews what we did before spring break, to what you guys learned about increasing interest. Do you remember what the formula was for continuously compounded interest?
Principal amount times E to
Woo!
A times time.
Sorry, I don't know what happened there. Yes, that's awesome, Jaden. Thank you. Let me get my thing back up. I don't know what happened. This is really weird.
Drag the black bar to the left side.
This thing? No.
Yeah.
The black bar? This thing?
Yeah. No.
Wait.
The black bar.
Oh, I got you. I got you.
And then it should-
This thing? This
Yeah.
thing. What did I do?
Almost there.
Ah, you guys are amazing. Yes, okay. So Jaden's right. It was the amount is equal to principal times E raised to the interest rate times T. Now, what you had to remember was P was principal, R was your rate of change, T was time. Well, when we would graph something that's gaining interest, we would get a graph that models exponential growth. There's another scenario that models growth or decay, and that's in populations. Oh, thank you. I can't. Sorry, I'll hold it there. This was just for continuously compounded interest. You're going to recognize that the formula today for population growth or decay is extremely similar. And that's because as we investigate something that's increasing over time or decreasing over time, if it's decreasing or increasing quickly, just we kind of have that E number come up again, and you have a formula that works in a similar way. So let's look at the formula. We're going to see how it works, and you're going to find it just very similar to what we did before spring break. So this is the equation for exponential growth or decay, and specifically we're looking at a population. So what do these these values refer to? N of t refers to the amount of population at a given time. Amount of population. N of O, that's your initial population. Initial population. E is the number that comes about as a population increases to infinity. K, this is kind of weird, and in some books it's called R. K is the rate of change. So how quickly is the population increasing or decreasing? The rate of change. And then what do you guys think T is? Yep, T is the time. So it's kind of like PE to the RT, because P represents your initial amount, your principal, times E raised to R is still your rate of change times time. So you technically don't have to memorize a new formula, you just have to know how these new values work with population. Here's the steps that we would use to solve, and then we'll go ahead and we'll just try a few together. Number one, you're going to use the given T value and population value to solve for K. You have to solve for your rate of change first, and a lot of problems don't tell you to do this. And that's kind of the like hidden, like, hey, I need to know to do this first. I have to see at what rate is it changing. Then number two, you'll plug the K value into the general formula and then use the general formula to solve for the unknown. So let's try this with number one. Number one says the number N of T of bacteria in a culture is modeled by N of T equals 100 times E raised to the K times T, where T is time in hours. If N of T is equal to 300 when T equals 5, estimate the time required for the population to double in size. So the first thing to do, and I'm going to go ahead and even write that off to the side, just because most problems don't tell you, but just go ahead and write in, most problems don't tell you, you must solve for K first. You must solve, let's zoom in on that, for K first. Okay, so let's use what we're given. We're given that equation which models this specific population. We have N of T is equal to 100 times E raised to the K times T. And what can we use to help us solve for K? Excellent. When N of T is 300, T is equal to 5. So basically, N at 5 is equal to 300. So 300 is equal to 100 times e raised to the k times, what can I plug in for t? 5. Now we need to solve for k. You're going to notice that k is in the exponent. That's why we looked a lot at solving exponential equations on Tuesday and even today in the group work. So what would we do first to solve this exponential equation? Divide by 100. So we have 3 is equal to e raised to the 5k. Now what do we do to solve? ln both sides. And we have ln of 3 is equal to, what do we do with that 5k? Becomes a power, and what is ln of e? 1, so what's 5k times 1? Just 5k, good. And then we would divide by 5 to both sides. And now we have the value of k is equal to natural log of 3 divided by 5. Now you're going to want to store this number into your calculator so that you can use it later in the formula to help you solve for the required unknown. Does anybody know how to store a variable? I'm going to write the commands that you would press in your calculator, and then we'll do it together. So to store this, you would press the button STO and then alpha, A-L-P-H-A. You guys know that. And then parentheses. So take out your calculator, and we're going to store this value. So we would do, and oh gosh, it's been a while since I've done this. I don't know if we press the number first or if we do, yeah, we need to press the number first. So you're going to put in ln of 3 divided by 5 into your calculator first. So ln of 3 divided by 5, you can press enter. And then you're going to store, so press that series of commands, STO, which is underneath, you guys can't see this, it's underneath your ln button is STO. And then you guys know where alpha is. And then you'll do the left parentheses and it'll bring up k and press enter. And now what happened is your calculator stores k. So we just have k is a button now on our calculator. Now k is being stored. Stored as a button. Yeah, and you'll have to do this every time you plug in k into your calculator. Okay, now we know the rate of change, so we know what function this bacteria culture is modeling. So if I go back to my function, I can fill in the value of k. I know that n of t is equal to 100 times e raised to that value of k, which I stored on my calculator, natural log of 3 divided by 5, times the time. So now I know the specific function that this is modeling. And so just so you guys are aware, we've stored this, so now we can use it at different points in our problem. Okay, now it says, if n of t equals 300 when t equals 5, estimate the time required for the population to double in size. What did you say? 600 is the time? Oh, well, what is the initial population? That would be a population when time equals 5. You're right. So if you wanted to use that, you would have to say 600. So yes, the doubling of the population. Right now, the initial population is 100. So if we want it to double in size, what do we have to set the left side of the equation equal to? 200. We want to see when does it double in size. So if we want it to double, we need to double the initial population. We need to double 100. So now we have 200 is equal to 100 times e raised to that stored k value times t. And now we need to solve for time. So what would be our series of steps? What would we do first? Divide by 100. And that gives us 2 is equal to e times to the stored k times t. What would we do then to solve for t? Natural log. We got to get that variable out of the exponent. So we do natural log both sides. And now we bring the power, we use the power property to bring k times t in front of natural log of e. But natural log of e is just 1. So we have natural log of 2 equals that stored k value times t. And now what do we do to solve for t? Divide by the stored k value. Yep. So in my calculator, I will just go to natural log of 2 divided by, and then I'm going to choose alpha parentheses to get that k value that I stored back in. And I'll go ahead and switch to the screen for a moment just so you can see my calculator. I did natural log of 2 divided by alpha parentheses for that stored k value. And then what should the time come out to equal? 3.15 years. Hours, sorry. What's the time? Hours, thank you. So the time is approximately 3.15 hours. Yeah, because we rounded. Any questions on that? Catherine? You didn't get that into your calculator? Okay, I'm going to pause the video just for a moment. Have you guys just try the second one, read through, see what you can do. And then I just want to come around and make sure everyone is good with their calculators. Hey guys, as we're working, I want to make sure we understand this new vocabulary. Some people, depending on where they've been in their science, we just want to make sure we clarify this. If it says given that the radioactive isotope radon has a half-life of 1620 years, that means that it takes 1620 years for the population to cut in half. So you might want to write that if you didn't know that. I originally didn't know that. It's been a while since I've been in science. So I had to kind of go back and look and say, what is a half-life? So that means it takes 1,620 years for the population to cut in half. So this population, unfortunately, it's dying. It's going away. So what does that mean our rate of growth should be? A positive or a negative number? Negative, yeah, because it's decreasing. Okay, so letter A says, what must the K value be for this particular isotope? So we know that we have to solve for K first. We know that our formula is N of T is equal to N of 0, the initial population, times E raised to the K times T. Now, if I was looking at the initial population of, for example, 1, so let's just call it 1, for like maybe it's 100, maybe it's 300, maybe it's 500. What would be the half-life? 0.5. So I have 0.5 equals 1 raised to the, or times E raised to the K times, what should be the time? Yep, it takes 1,620 years. So this would be the place that we have to start at. And that does help, that does make us recognize that whatever the initial population is, could I have technically entered 10 and 5? Yeah, I could have entered 20 and 10. I could have made up an initial population. But since I'm looking at the half-life, I need to decrease it by a half. Because when you start dividing in your problem, it always reduces to a half anyway. Okay, do you guys want to keep going on your own or keep going together? On your own? Okay, go ahead and finish this, and then we'll go ahead and take a look at our answer. Few things to check. Make sure you have K correct. Natural log of 0.5 over 1620. Letter B, your function just contains the rate of change. So it's just showing what the function would look like with this specific rate of change. Letter C, you're finding the number at 1,000. You're finding the population after 1,000 years. And then letter D is using the initial population from C. You should be the time to be approximately 4,433.8 years.
B, don't we have to solve for T?
No, B is just writing a function. A function just is really in terms of two variables. So you're saying that the actual population is going to equal the initial population times e raised to that k value times t. So it's just showing that your function is what we're using to solve.
Okay.
Jeremiah?
You need to have that box to indicate that. Like,
No. Well, I mean, you could have this value instead. But you do need to have the k reference that you found it. Good stuff. Anybody else? Other questions? Okay, let's try this last one together. A culture starts with 8,600 bacteria. So what could I call that in terms of the formula? N of 0, kind of like P. After 1 hour, so when the time is equal to 1, the count is 10,000. So N at 1 is equal to 10,000. Find a function that models the number of bacteria after T hours. You guys want to try this on your own with your group? Yes, and then check the answer. Sounds good. Let's do that. Okay, your homework is from the book. Make sure that you look at the book. Don't work on the group work. You don't have to. You can, but it's due Monday with additional group work.